Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of a final series of videos on graphing using calculus. Notice it says part 6 because parts 1 through 5 were including all of the stuff except for symmetry and oblique asymptotes, or slant asymptotes if you want to call them that. We talked in the previous video about oblique or slant asymptotes and how to find them. The only other thing that's new here is that we are going to include something called symmetry, which you should know from many algebra courses. It just basically is the function odd or even. So is it symmetric? Also, we'll look at periodic functions. However, periodic functions are not as common, so I don't want you to really freak out about it. However, it is useful. It can be very, very useful. So I'm not going to downplay it. I will look at each function that we're handed in this series of videos, because I'm going to basically do one graph per video to keep the videos less than 5 hours, basically. And we'll go ahead and consider all of these steps, each function. So I will ask, is this periodic or symmetric or something like that? So given a function, how do you accurately graph that function? You can think of this in terms of how you learned mathematics. So this first step right here is from your elementary algebra or beginning algebra or algebra 1, right? Algebra 1. That's where you find your intercepts. Little note about finding intercepts. These two words are very important, if possible. If you're working on an exam and your instructor does not allow you a calculator, often finding x-intercepts are incredibly difficult. Y-intercepts not so much, but x-intercepts can be very challenging if your instructor has accidentally given you a terrible problem. Okay, so that's just a heads up. If they do give you a problem that the x-intercepts are nigh on impossible to find, in other words, if it requires you solving something like, remember, you find x-intercepts by letting y equal 0. So if your function's the following, like x squared plus e to the x minus the natural log of x or some silliness like that, and then you set it equal to 0, find the x-intercepts, you're not going to be able to find that by hand. There are techniques to help you. There's something called Newton's method, but in the calculus book that I use and that most of the nation uses actually, Newton's method is not covered until after you're done graphing, which is sort of weird, and I'm kind of thinking it should be taught first, but okay, not a big deal. Anyhow, so just know when, this kind of goes back to a song from the 80s, know when to hold them and know when to fold them, right? Know when to walk away and know when to run. So in this case, you got to know when to walk away from finding an intercept when it's impossible. If it's a mixture of functions equaling 0, often by hand, it's impossible to find. Usually your instructor should be kind enough to let you know that. The next thing you're going to do is go into your algebra 2. Your algebra 2 is where you started talking about functions. And actually, technically, a lot of students are coming up nowadays in the Common Core era, so they may not have ever had algebra 1 or algebra 2, but it's equivalent, whatever. You learn it in this order. So find the domain of your function. This is going to be very important for the entire graph, because it really can restrict the amount of graphing you have to do. The next thing we're going to do, and this is new in this video series, at least, find the symmetry. Find out if it's odd or even. Again, this is algebra 2. So again, I'm still climbing through my algebra ladder. We're going to state whether the function's odd, even, or periodic. So odd or even or periodic. So all those years in algebra classes where they said oh, is the function odd, even, or neither? It's really to build up to graphing. And here we are, we're going to use it quite a bit, because imagine if your function is even, then it's going to be symmetric about the y-axis. So if it's some silly, terrible looking function that's actually not bad looking on one side, then all you need to do is graph one side of it and then just copy that graph to the other side. So it reduces your work by 50%, because 50% of your work is just graphing the right hand side of the graph, and then because you know it's even, copy it over to the other side. And there are tactics associated with that. Same thing if it's odd. If it's periodic, well, same thing. Just graph a single period and then copy and paste. Now we're going to climb into pre-cal mixed with calculus. So this is, I'll still call it pre-cal, both of these in fact, but in reality, you're technically using calculus. So vertical asymptotes. You learned that in pre-calculus, but you're going to use calculus because you need to, after finding the vertical asymptotes, you need to find the behavior near those vertical asymptotes using limits. So use limits. So if you know that, for example, x equals 3 is a vertical asymptote, take the limit as x approaches 3 from the left, find out what that value is, and take the limit of your function as x approaches 3 from the right. That gives you the behavior around that asymptote. You might say, yeah, but can I use the multiplicity of the asymptote? Well, not all asymptotes come with multiplicities. Think about like tangents and natural logarithms. They don't have multiplicities. So you cannot just say, oh, every vertical asymptote has a multiplicity. It doesn't. So it's better to use calculus because you won't have the multiplicity from rational functions for use here. And then the final pre-calculus step. In pre-cal, we learned what a horizontal and oblique asymptote, or what horizontal and oblique asymptotes are, is what I should say. And so you're going to use limits. This is basically the end behavior, honestly. So this is end behavior, and you're just going to take the limit as x goes to positive or negative infinity. If it's a horizontal asymptote, then, well, your limit would be a finite number. If it's an oblique asymptote, you'll have to prove that it's an oblique asymptote using the methods provided in the previous video. So that's your pre-calculus step right there. Now we climb into calculus. So all of this right here is your calc, all the new stuff. So really half of your work is prior to calculus and the other half is after or with calculus. And all of this is just computing the first derivative, the second derivative, determine intervals of increase and decrease where the derivative is positive and negative. Use the first derivative test to indicate local extrema if possible. Second derivative test, right? Take the second derivative, determine intervals of concavity where the second derivative is positive, where it's negative. State inflection points where concavity changes as long as your function is continuous. And then use the second derivative test to indicate local extrema if necessary, if you couldn't do that with the first derivative test. Always organize your information, and finally, graph. These problems take quite a while to do. So do not feel intimidated if you spend 30 minutes working on one of these problems. That's just how these problems are. You cannot avoid that if you're going to be accurate. It's very obvious when a student spends 5 minutes on a problem like this because it's sloppy, it's terrible, and it's worth nothing. Spend some time. Really try to understand what's going on. Trust me, on an exam, I don't know your instructor, but trust me, if I was your instructor, that I wouldn't hand you 5 of these problems on an exam. That would take you way too long. I generally like to hand 1 of these problems and then a concept problem or something like that. So let's go ahead in the remainder of this video, just spend that time graphing 1 function. Now, please be careful. That is a cubed root, not x to the third. It's kind of hard to tell in some of the graphs, but anyhow, I don't have a laundry list of things here. You can see it's a big blank page. So I have to remember kind of the order with which I learn things. And it's okay if you do things out of order. It's just that the symmetry is nice to do early on so that you know you don't have to do a ton of work. I usually don't I save symmetry until maybe the third step or something like that, but I still tackle it pretty early in the process. All right, intercepts. So the easiest intercept is the y-intercept. I try to give myself a win. Y-intercepts occur when x is 0. The problem here, actually it's not a problem at all, x can be 0. If x were 0, you get 0 times who cares. And by the way, you can take the cube root of a negative number, so totally fine for x to be 0. All right, so when x is 0, y is 0. I'll go ahead and write that as my y-intercept, 0, 0. Once I get a point going, for organizational purposes, I will order all of my, I'll build a table, I should say, off to the right or the left or someplace clean, basically. I don't want you to think that I'm always looking to the right-hand side of my page, but I suppose in all my lectures, that's what I've done. Now we look at x-intercepts. Well, x-intercepts occur when your function is 0. And so we'll solve 0 is equal to x times the cubed root of x squared minus 4. Well, either the first factor is 0, and we have that listed already, it's right there, but I'll write it down here because my students use an online homework system, and if it says list out the x-intercepts, it expects all of them. So there's the first one. And then this stuff turns into 0 when x is equal to plus or minus 2. So the next two x-intercepts are going to be 2, 0, and negative 2, 0, which gives me some hope here because notice they're symmetric about the y-axis. So this function could be odd or even. That'd be kind of neat. All right. And usually, by the way, I don't like to take up a lot of my paper with computation because I'm trying to do my graph on the same page. You don't have to, but I'm just telling you that's what I'm trying to do. So I'm going to shuttle my work up a little bit just so that it's compressed. Now I'm going to move on to what is the domain. Well, the domain here is all real numbers because you can plug anything into that function. So there's no domain restrictions with this function. You can easily see that because you can take the cube root of any number. So the domain is all real numbers, which gives me even more hope that it might be symmetric. So I'll go ahead now and look at symmetry. Symmetry. And symmetry, I will look at g of negative x. That's how you will always have tested for symmetry in the past. And actually, I'm going to do all my computations in, I should have just done all my computations previously in blue. There you go. I wrote over it in blue. So now I'm going to go ahead and do this computation to see the symmetry. I'll do that in blue and I'll state the symmetry in black to the left there. So I'll look at g of negative x. Well, let's take a look at g here. That's x times the cube root. So it's negative x times the cube root of negative x squared minus 4, which is equal to, let's see, a negative x times the cubed root of, well, a negative x being squared is just an x squared minus 4. And if you take a look at this expression, that is actually the opposite of g of x. So this is the opposite of g of x, which tells us if g of negative x is negative g of x, g is odd. And that is going to be super powerful and also something that I'll often forget. When I say that I'll often forget, what I mean is that as I'm doing my computations, because this is such a small part, I tend to forget that my function I'm dealing with has symmetry. I need to remember that. I'm going to highlight that just so that I remember that. I know my weakness. You should know yours. All right, the next thing we're going to do is, let's see, we've done our intercepts, we've done the domain there, we have the symmetry. Let's step into pre-calculus and talk about any horizontal or oblique asymptotes. And I usually start with, honestly, vertical asymptotes. If your domain is all real numbers, it's very fast just to say vertical asymptotes do not exist, or none, whichever you prefer, because the domain's all real numbers. So I don't have any domain issues. That's why I like to start with vertical asymptotes before I go to horizontal or obliques. Horizontal versus obliques, or slants, whatever you want to call them. you would let x go to infinity in our function. Again, I'll do my work over on the top here. The limit as x goes to infinity of g of x, you could see here, if you allow x to go to infinity, you'll get infinity times infinity, basically, and that's infinite. So we definitely do not have a horizontal asymptote. And because nothing disappears, we also don't have an oblique asymptote. That's a quick way to say that. Since nothing disappears, there's no chance for an oblique. And since this limit doesn't become finite, well, there's no horizontal asymptote. But it does give me a good piece of information. The fact is, as x goes to infinity, I know that my y values are going to rise forever. So I might as well just get a little good piece of information as x goes to negative infinity. And just quickly looking at the function, if x was going to negative infinity, I'd have a negative infinity out front. And negative infinity squared is positive infinity, minus 4 is still positive infinity. So you get negative infinity times positive infinity, or in other words, negative infinity. It's not always the case that it's super easy to find those values or to find what the tendency is. But if you can, and since nobody's asking you to do it, if you can do it, do it. It's a good idea. Anyhow. All right. So oblique and horizontal asymptotes, because it doesn't become finite and because nothing disappears, these do not exist. Notice that we've gone through all of the algebra and pre-calculus that quickly. There's nothing really crazy about this. And now we get into the crazy part though, because now we're going to go into the derivatives, right? We want to know where we have intervals of increase, where we have intervals of decrease, where we have local maximums, where we have local minimums, all that stuff. So I will go ahead and take the first derivative here. So g prime of x is equal to, you could see it's going to be a product rule, which is always a little bit of a daunting issue just because people don't like to do that in graphing. It's just a pain sometimes. But we have the quantity, derivative of x, which is 1, times the quantity of x squared minus 4 to the 1/3, plus x times the derivative of x squared minus 4 to the 1/3 power, which is 1/3, times x squared minus 4 to the negative 2/3 power, times 2x. And we want to ask ourselves, where does that derivative not exist and where does that derivative become 0? Remember, you want to find the critical numbers of g, and that's where the first derivative does not exist or where the first derivative becomes 0. Well, in this case, it's better, I think, to combine this up into a single statement. So I'm going to go ahead and glue these together. Although I can easily see where this will not exist, it still will be helpful to combine things up into a single statement. So if you can imagine, this is x squared minus 4 to the 1/3. So all your algebra comes into play here. Plus, let's see, we have 2x squared over 3x squared minus 4 to the 2/3 power. If you're really bad with algebra, this is not going to be fun for you. I'm going to multiply numerator and denominator of that first term by 3 x squared minus 4 to the 2/3 power. And when I do that, I get 3 times x squared minus 4 plus 2x squared all over 3 times x squared minus 4 to the 2/3 power. I've often thought that this material would be much better to teach at the beginning of a calculus course because it would really let people know where their weaknesses are with algebra. But unfortunately, you need to go through most of calculus to get to this. So, oh well, such is life. That becomes a 5x squared minus 12 over that 3 times x squared minus 4 to the 2/3 power. This is also incredibly helpful for when you take the second derivative, by the way. All right, so where does this not exist? I know that it doesn't exist when x is equal to plus or minus 2, because that's when that derivative just doesn't exist. So I'm just going to say maybe off to the right-hand side here, just to reserve room. And by the way, don't try to squeeze a graph into a small space. If I can't get my graph to fit in this space right here, in the space to the right, then I'll just open up a new page. That's perfectly fine. Don't try to squeeze a graph into a small space if it's not going to work. But here I know G prime does not exist at x equals plus or minus 2. I also know that G prime is equal to 0 at, let's see, when that numerator is equal to 0. So when x is equal to plus or minus 12, the square root of 12 fifths. So x equals plus or minus root 12 over 5. If you're not allowed a calculator, that's going to be somewhat of a pain. That's just how life goes, though. You just kind of have to suck it up and invent numbers, I guess. But that's it. Also, notice there's a lot of places for little arithmetic errors. That's always been the case. Just be very careful as you go through these problems. I then create a number line. Now, here's the deal. I know that G is odd, and that's why I say often I forget it because you're doing a lot of computation. But if you can remember that G is odd, then just start at 0. Because you know it's gonna, sorry, I just swept my hand across my screen. Because you know that the graph is going to be symmetric about the origin. So whatever you graph to the right-hand side of 0, you'll just spin it around 180 degrees, and you'll get that graph on the other side of 0. So let's worry not about the plus or minus 2, but instead just the plus 2 and the plus square root of 12 over 5. I can tell you right now, the plus square root of 12 over 5 is less than 2. At least I know that. So I'll put the positive square root of 12 fifths right here. And I'll put an open circle right here for positive 2. And a number that's less than the square root of 12 over 5 is 1, because that'd be the square root of 5 over 5. So I'm going to plug 1 into G prime. Remember, G prime is actually this statement right here. It's a little bit easier to compute there. So if you plug 1 in, you'd get a negative number on top. And note that denominator, because it's the cubed root being squared. The squaring part is the important part. Because that denominator is being squared, it's always positive. So I know the denominator is always positive, but the numerator, when you plug 1 in, is going to be negative. And so we have the derivative is negative there, or in other words, our function is decreasing there. Now we're going to plug in a number between square root of 12 fifths and 2. Now that's going to be tough, because if you don't have a calculator, it's going to be very difficult for you to know what is a nice number between the square root of 12 fifths and 2. And this tends to throw people off. Go ahead and grab a calculator right now and compute the square root of 12 fifths, just so you can get an idea of the size of that number. It's a little greater than 1.5. So I'd like to plug in a number slightly greater than 1.5 into my derivative. And if you just have a calculator, you could do it very quickly. Plug in 1.9, for example. So 5 times 1.9 squared, I'll just do it this way, minus 12. Oops, I put plus on my calculator, minus 12. So the numerator is positive in that instance. And the denominator, remember, is always positive. So we get that the derivative is positive there, or in other words, the function is increasing there. Be very aware your derivative does not exist at 2. That means either your function went vertical right there, or you have a kink in your function right there. Or if your function is not continuous, which our function is continuous, if you take a look at our function is continuous. But if your function wasn't continuous, you could have had a jump discontinuity there. So this is either an infinite slope, or, in other words, a vertical tangent, or you have a kink cusp or corner there. Let's see, and we'll figure that out as we go to the graphing part. But you can plug any number greater than 2 into the derivative, and 3 is a fine number to plug in, or a billion is also good. Either of those will work out well. You'll get a positive value. Whoops, wrong color. You get a positive value for your derivative there, so your function is increasing. So now I know I have pretty much everything I need. Notice that I'm not really filling anything out in black ink over here. That's because honestly, this step is more about just listing out this nice clean chart here. I'll label on this chart that where I have minimums and maximums. So we know we have a local minimum at square root of 12/5. And so what I'm going to do is I'm going to start adding these values to my table. And I should have also added, by the way, my x-intercepts to that table. So the x-intercepts I will also add, although I'm only going to do, because we have an odd function, I'm only going to do the positive x values. Because it's an odd function, we can rotate around, we'll get the negative x values. Let's see. The next critical point occurs at the square root of 12/5. So I'll plug that in here. Square root of 12/5. Remember, we have one at negative. We also have a critical number at negative square root of 12/5, but we're going to use the fact that our function is odd here to get that. And then let's see, we also have 2, but 2 is, well, already there. I will say maybe here I might make a note to myself. F prime or G prime, sorry, does not exist. If G prime does not exist, G double prime will not exist as well at that point. So G double prime does not exist there as well. It's just a little note to myself. It's not necessary, but I just like to do that. Once you find that point square root of 12/5, it's probably a good idea to plug it in. The problem here is that it's going to be a decimal value. Again, if you have access to a calculator, you could do this. If not, it's a little bit of a pain in the butt. I'm going to go ahead and pretend as though you're allowed a calculator so I can get a decimal approximation. So that x value is approximately 1.5. And then the function at that x value, it is approximately negative 1.8, very approximate. And by the way, I'll also note that that is a local minimum. A local minimum. Write that in here, Lmin. All right, so first derivative down and done and completed. Now I'll go to the second derivative. So the second derivative, maybe I'll do the second derivative in a different ink so that you can see my handwriting. Now I'll just continue with this blue ink. G double prime is equal to. I'm going to use this version of G prime because once you get a quotient, even though a lot of students hate the quotient rule, and I actually am with you a little bit on that, I'm not a huge fan of it. When it comes to graphing using calculus, leaving it as a quotient and using the quotient rule is a good idea. Just because it keeps things nice and clean and factored. So the derivative of that numerator, which is 5x squared minus 12, is going to be 10x times the denominator, which is 3 times x squared minus 4 raised to the 2/3, minus the numerator, which is 5x squared minus 12 times, let's see how ugly this is already getting, the derivative of the denominator. Well, the derivative of that denominator is going to be 2/3 times 3, or in other words, 2, times x squared minus 4 raised to the negative 1/3, and then by the chain rule, 2x. In the denominator, you're going to square that. 9 times the quantity x squared minus 4 raised to the 4/3. Now I'm going to multiply both numerator and denominator by x squared minus 4 to the positive 1/3 to get rid of this silly negative 1/3. So I'm going to multiply top and bottom by x squared minus 4 to the positive 1/3. And I'm taking my time with this because, well, it's probably a good idea because this can be a very, very messy process. So I'm just going to increase all the powers in the numerator on the x squareds minus 4s by 1/3. So that just becomes an x squared minus 4 to the 3/3 minus 4x times the quantity 5x squared minus 12. And then obviously that disappears because we've multiplied it by the same thing to the power of positive 1/3. All over, we're going to add 1/3 to the power on this denominator here. So it's a 5/3 power. Now note, the 5/3 power is a dangerous power because now that denominator could be negative. So now we do have to consider the negativity of that denominator when we're looking at whether or not it's the function's concave up or concave down. If you don't understand why I said that, it's because when we looked at this one, the first derivative, I had said, well, that denominator is being squared, so it's always positive. So we only really looked at the numerator the entire time. Once that denominator has an exponent with a numerator that's not even, well, now you have to always investigate the signs of that denominator as well. Distributing through in the numerator, we will get a 30x cubed minus 20x cubed, or in other words, a 10x cubed. And let's see what else we'll get. A negative 120x plus 48x, which is a negative 72x. And this is all over a 9 times x squared minus 4 to the 5/3 power. It's not really going to help me if I want to factor in the numerator yet, so I'm just going to leave it like that for now. And let's go ahead and investigate this double derivative. G double prime does not exist when, again, x is equal to plus or minus 2. But because it's odd, I'm only going to worry about the plus 2. Okay. And G double prime is equal to 0 when, and again, you would set that numerator equal to 0. 10x. Now I'll go ahead and factor actually. Both of those have 2x in common, so you're left with a 5x squared. Let's see, minus 36 maybe? That sounds about right. Let me just double check. Divide by 2, divide by 2. Yep. And this is 0 when x is equal to 0, or when x is equal to plus or minus 6 over root 5. Pretty terrible, actually. Not the best problem ever, but actually really good problem to showcase that you can do this even though the numbers are horrendous. I'm just going to grab a calculator to approximate these values. Now we'll go ahead and graph out or place a number line here. So we have G double prime. We can put 0 right here because, well, again, G is odd. So we're just going to graph the right-hand side and then rotate it about the origin 180 degrees to get the other half of the graph. So really the best part of the graph is going to be the right-hand side. The sloppiest part, which will not be sloppy, but will be not as accurate, will be the left side of the graph. And your instructor may require you to actually graph both sides, to show accuracy on both sides, but I'm kind of lenient on that and just say, if you have symmetry, graph perfectly one side, and then you can rotate that about or reflect that about to graph the other side. Anyhow, let's go ahead and plot where our second derivative does not exist, which is at 2. I'll use red for that. And actually, I think I have to figure out what this 6 over root 5 is, so give me a moment. So 6 over root 5 is greater than 2, so I'm going to plot that first, actually. So 6 over root 5 I'll put here. 6, that's supposed to be a 6, but for some reason it just didn't work out. Root 5. And then the 2, just underneath that right there, that's where the derivative, second derivative, does not exist. And then obviously 0. So you have 3 parts of this interval. And I do want to mention here, it's very, very common for students to forget to plot on this number line where the derivative doesn't exist. You want to include that information because if you don't, your graph is likely going to be really, really wrong. So let's grab a number between 0 and 2. 1 is a perfectly fine number, and we'll plug it into this second derivative. Plugging 1 in, you get 10 minus 72, which is negative. I'll write that up. So G double prime at 1, we get a negative value over, and 1 minus 4 is negative, and you're raising it to an odd power, so it remains negative. So the denominator is negative as well. Negative over negative is positive. You have a curve that is concave up on that interval. plug in a number between 2 and 6 over root 5. 6 over root 5 is roughly 2.7. I'm just going to actually squiggle that in here, right here. So roughly 2.7. And so if you plug in like a 2.5 or something like that into your second derivative, I will go ahead and do that and just tell you what it's going to be. So g double prime of 2.5 is approximately, actually I don't even need to say approximately. Computing it out, g double prime of 2.5 is negative. So we have this negativity here, and that means our curve is concave down. Finally, any number beyond 6 over root 5 or beyond 2.7, and I'm just going to plug in a trillion. A trillion cubed times 10 is massive. Minus 72 trillion is still pretty positive, divided by a positive number. So it's going to be positive. So we have concave up for our function. We have almost everything here. One thing to note is that our function changes from concave up to concave down at 2. So the 2 is an inflection point. Our function's continuous there. And it switches from concave down to concave up at this 6 over root 5. So that's another inflection point. I will add 6 over root 5 to my table. So let me go over to the table up here, and I will zoom in wherever it is, and I'll put in 6 over root 5. Oops, darn it, I've done that twice. 6 over root 5, which is approximately 2.7 is what I said. I'm asking you, but you can't respond to me because you are not talking to me right now. And I'll also maybe mention here that this is an inflection point, but to be honest with you, that'll be taken care of when I graph my number lines up above. And I have to evaluate g at that 6 over root 5. So let me do that. And I get roughly 4.0, and this is an inflection point. It's a little bit less than 4.0, but whatever. And so this table of values is going to be very helpful for me. Notice I'm only going to plot 1, 2, 3, 4 points, and I should get a very accurate graph just from plotting those 4 points. Pretty interesting. Now I'm going to start the graphing process. I'm going to use the fact that it's odd. I'm only going to graph the right-hand side, and then I'll reflect that about the origin to get the left-hand side. Now I want you to see the setup that I use here. I graph a set of axes well below, okay? And I'm actually graphing the full Cartesian axis there, like both positive and negative x values, because that's eventually what I'm gonna do. But notice my number lines up above. If I'm gonna use symmetry, I only wanna look at the positive x values there, because if I draw out the whole thing, I'm going to confuse myself. So it's a little bit better for me to just go ahead and only use the symmetry that I have in place and do that. So this is kind of the base setup that I do here. And I'll label the top line there, horizontal line, I'll label that G prime, and the second line I'll label G double prime. So let me label this G prime and this G double prime. And then I will place on those lines these numbers, root 12 over 5 and 2, and the other one, 2 and 6 over root 5. So let's go ahead and do that. And I'm going to use my table here to help me kind of gauge where those values are. So we need my x values to go all the way out to about 3. I'll go all the way out to 5. How's that? So I'll just pretend as though this over here is about 5, and that way 2.7 is roughly right about here. So that's going to be 6 over root 5. And that was important for my second derivative. And 2 is going to be right about here. That's important for my first and second derivatives, actually. And then 1.5, which is important for my first derivative, is probably right about here is my guess. And that's the square root of 12 over 5. And then I'll just label the concavities and stuff like that. So we have decreasing here. I'm just looking to the left. I'm looking actually right here. Decreasing, increasing, and increasing. Interesting behavior there. I know this is a local min. Let's see, the other piece of information I have down here, concave up, concave down, concave up. Okay, concave up, oops, concave up, concave down, and then concave up. And obviously this would be an inflection point, and that would be an inflection point. Now I'm going to plot the values that are in my table. So I'm going to plot 0, 0, and 2, 0. I'm going to use a ruler to help me out here. Where'd my ruler go? So I want to plot 0, 0. I'm going to do this graph in green because green is good. 0, 0. And line up those 2's. So 2, 0. I'll plot that point as well. There we go. I'll label it 2, 0. 0, 0 is obvious. I don't need to label that. And let's see what else is in my table. 1.5 comma negative 1.8. So 1.5, which is right about here where that root of 12/5 is, and a negative 1.8. I haven't labeled my y values yet, so let me take a look at these y values. Let's see, the highest y value I need is 4. So you know what I'm going to do? I'm going to go ahead and maybe do this. I'll call this, I think, I don't want to use green to do that. I'll use black. I'll do these hash marks like this. I have to get my ruler kind of close. Getting close here. 1, 2. That's all I really need on that. And 1, 2, 3. Notice how accurate I'm trying to be. Okay. So let's see. I want negative 1.8 at x equals 1.5. So let's go ahead and line this up. There's x equals 1.5, and I want about a negative 1.8. Should probably be about here, maybe. And I should use green to really put that in there. And this again is root 12/5, comma, roughly, right? Because we don't know. I didn't really exactly compute that, so it's roughly negative 1.8. I'll just put negative 1.8. I think that's very fair. All right, so we get that. And then what else do we have? Oh, it's in our table. 2.7, which is at 6 root 5, comma 4. We zoom in. Line that up. So it's right about here. That number, I can now turn off my ruler. That number is, the x value is 6 over square root of 5. The y value is approximately 4.0. Now I'm going to start graphing. It's decreasing and concave up between 0 and that first point I plotted. So kind of scratch this in here. It's going to continue to be concave up after that, but start to increase. So I know that it's going to have a nice smooth bottom there. Darn it, I have to zoom in. My hand keeps moving my screen. Sorry, left-handed people should understand my plight. All right, it's going to be increasing and still be concave up in this interval. It'll switch to being concave down, but still increasing after I get through this. So it's concave up all the way there, and then it switches to concave down. It's a very gentle switch, by the way. And it'll be increasing and concave down until I get to this inflection point. So I'm going to go ahead and try my best to mimic a concave down behavior. Man, that is good looking. And then it's going to switch to increasing concave up for the rest of the trip. There we go. And because this function is odd, I can rotate it 180 degrees to get the rest of the picture. So this is your accurate part of the graph should be the right-hand part when you're using symmetry. The rest of it's going to be kind of a little bit of eyeballing. Try to be somewhat good about it. So I'm going to go ahead and try to do this somewhat accurately. So it's concave down, something like this. And I had to check to see if I was recording. I've done this, not this specific problem, but I've done it in the past where I've thought that I was recording and I wasn't. I had to re-record a whole entire lecture. That sucked. Something like that. So I'm going to do this. and then it switches. Concavity at that point. Something like that. That looks to be odd, and look how beautiful that graph is. Now, I almost walked away from this video without mentioning something here that I need to mention. Remember when we were taking the derivatives and stuff like that, we said, oh, the derivative doesn't exist at 2, so we're likely to have a kink, a cusp, or maybe the tangent line goes vertical just for a moment at 2. And notice at x equals 2, gosh, I almost totally forgot this, but notice at x equals 2, the graph actually is supposed to go vertical, momentarily goes vertical right there. So that is a critical element of this. It's just something that I almost walked away from this problem forgetting, because often it's very easy to forget that little step there. But it is kind of important to remember why that derivative doesn't exist at 2. It's one of really two major, well, one of three reasons really. Either the graph goes vertical momentarily, or you have some type of corner or kink or cusp there, or you have a jump discontinuity. Our function was continuous, so we don't have to worry about a jump discontinuity. And the way the graph ended up, it's not like we had some jaggedness to the graph at x equals 2. So it is a vertical tangent. It goes vertical just momentarily. Very, very hard to see that, and I wouldn't blame you for not seeing that, but it totally does go vertical momentarily. So there we go. That finishes out completely the problem. Now we can move on.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.